That was until about 1964, when John Bell, an Irish physicist on sabbatical from working at CERN, started to do some more theoretical work of his own. These works, which were later called Bell's theorem or Bell's inequalities, of which there are many different forms, but the underlying idea is to try and get the universe to pick a side, tell us whether there's hidden variables and Einstein's right, or tell us whether truly there is a wave function and that quantum mechanics is real. Now this hinges a lot on what happens to quantum objects when you actually go out and measure them. So let me introduce you to the idea for a particle of light called a photon. Photons have a property called polarization, which describes which way the wave of light is oscillating through space, either vertically or horizontally, or potentially somewhere in between. If you wanted to measure which state a photon was in, you would put it through a polarizer that lets through either vertical light in one orientation, or it will only let through horizontal light in another orientation. But then at least your detector, which you place behind that polarizer, knows what sort of light it's detecting. If you fired in randomly polarized light, some of it vertical, some of it horizontal, some of it in between, by placing a vertical polarizer first, then a horizontal polarizer after, you would expect correctly to see that no light reached your detector because all polarization angles had been blocked. You can see this effect when using polarizing films, which are the same stuff you find on a pair of polarizing sunglasses. By orienting two polarizing films at 90 degrees to each other, you see no light emerges through them. What is interesting here is that if you place a third polarizer between these two, you suddenly, and I think quite counterintuitively, start to see more light. This is because fundamentally, measuring a particle changes its state, allowing light to slip through the final polarizer where usually it wouldn't be able to. So you start to see more light than you would otherwise expect. So let's jump back though into the story. At this point in history, Bell's work was still more theory and thought experiment than anything else. And that classically is the problem with theoreticians. If you look at them from a distance, it just looks like a wizard trying to have an argument with you. Physicists really needed to find a way of actually completing an experimental measurement. One of the early and most elegant and now heavily evidenced extensions of Bell's theorem work is the CH-SH inequality by John Clauser, the Nobel Prize winner that we're talking about here, Michael Horn, Abner Shimony, and Richard Holt. And their work here makes this theorem that Bell developed actually experimentally testable. The scenario they describe is similar to what we talked about before. Two entangled photons are sent in opposite directions to two observers, Alice and Bob. Both Bob and Alice get a polarizer to play with into their setup that helps them determine which polarization the light is actually in. And finally, Alice and or Bob, at random, are told to rotate their polarizers over time and record whether photons arrive successfully or not at their detectors. What we're interested in doing here is counting how frequently that Alice and Bob agree on whether they've seen or not seen a photon. If Alice and Bob perfectly anti-align their polarizers, then they should always both either see a photon or neither one should see a photon. They should always agree on whether photons arrived or photons didn't arrive. If, however, Alice and Bob both align their polarizers, either Alice should see a photon and Bob shouldn't see one, or Bob should see a photon and Alice shouldn't see one. The interesting part happens at angles between these positions. If the universe is real and photons are truly independent, Alice and Bob's rate of agreement should linearly move between full agreement and full disagreement. If, however, the universe is not real, we should expect to see a higher rate of coincidence than otherwise expected, just like in our three polarizer setup. Except now, our polarizers are on the other side of the universe from each other, and the same photon isn't going through both. Or is it? This can only be true if the particles are really still connected to let each other know which polarization state to be in, so that measurement on one truly does affect measurement on the other. And in 1972, it was John Clauser who built the first experimental setup capable of conducting this measurement. In the paper that he released that year, this was the figure that he displayed, exactly matching the prediction of quantum mechanics, proving that the universe isn't locally real.